infrared.
still alive.
And this can be compared with experiments. So that would be the idea of connecting experiments or phenomenology with quantum gravity from a realization group approach. And just before I close my talk, let me talk about old ultraviolet. Okay, it's okay. Let me talk about an old ultraviolet complete theory of quantum gravity. And well, I'm currently quite excited about this. So it's not very popular, but I'm going to talk about this, which is general relativity plus higher derivative terms. So the idea is that if you enlarge general relativity with higher derivative terms, then you change the behavior of the graviton propagator, and then you get a renormalizable theory to all orders in perturbation theory. So you can do, in principle, you can do perturbation theory with that. More than that, the theory is UV complete because there is a region in the parameter space where the couplings are asymptotically free. Why we are not celebrating? It's because this theory has ghosts. And for this reason, this kind of theory was, well, not seriously considered for several decades. But now there's a new perspective. Maybe these ghosts are not as scary as this one, but could be like Casper, a friendly ghost. So some perspectives on these are that in principle, this possible particle that we call ghost, this is actually a fake particle. This is the idea of fakions. There's also the idea of Marilyn modes, that these ghost particles are actually moving backwards, and for this reason, this would not cause any problem with unitarity. And my favorite one is that, well, I should actually have some quotation marks here, but the idea is that in principle, we have some conjectures that ghosts could be confined and would not appear as asymptotic states in the theory. So that would not cause problems with unitarity. Well, first, let me go to my final remarks. In this talk, I try to explain why that we need to quantize gravity. And the idea is that we came a long way on understanding the fundamental building blocks of our universe with standard model and general relativity. But both theories, they break down at very small distance or high energies. And one possible point of view, and that's the point of view that motivates me to study quantum gravity, is that quantum gravitational fluctuations may be the missing ingredient.
She and the group have shown
the question whether we have a theory of quantum gravity is yes.
Only compatible with the central.
We have the effective field theory paradigm. It's just, I mean, not UV complete. So we can do consistent calculations the Planck.
From Germany, Frank.
UV completion requires some change of paradigm. And there are many approaches to this problem. I try to mention a few of them here. It's still unclear if they are, if one of them, which one of them, or if any, is actually correct. And in general, we still have a long way to go. So we are not there yet.
So
with this, I would like to thank you
to the concept of a black hole. What is the definition? Well, a black hole is a region inside the boundary of the causal path of future null infinity. So it's a bit pedantic. A more intuitive way of saying this is a black hole is a region of no escape. Time diagram of
two slides, please.
This is space-time. Time is in direction.
One more.
Space in this direction, this direction. And so you see that things here go out. But
I was just curious to what exactly is this theory that you were talking about? Is it like Starobinsky? What are the higher derivatives? We'll consider a general scenario.
It's general relativity plus curvature scalar square plus Ricci square. So I mean U square plus R square.
This is
Okay,
the
Just
horizon,
R square, which is the Starobinsky
and the region,
model,
so
does not make it
region
renormalizable.
okay, fair enough.
called the black.
The effective Newtonian potential that you showed with the quantum correction,
Is space.
I was just curious to
time.
know up to
Space
what
figures that
energy
you see
scale
snapshot.
that correction
This
would
is
be
the
valid.
horizon.
Because surely it wouldn't work for Planck scale, but if not,
Well,
up
the,
to
let's
what energy does that hold?
Talk a bit
the upper bound is the Planck scale.
astrophysics of black holes.
The idea is that as
First,
you get close to the Planck
of
scale,
the
this approximation
black
starts to
hole
get
in the center
worse.
of galaxies.
Mhm.
But the upper bound is the Planck
So
scale,
since
because you need
63, it was
suppression
clear that
by these ratios
supermassive
here.
object
It essentially
nucleus
means that
are
this
quasar,
ratio has to
and
be
then people
smaller
got
than
to
1.
see active
Okay,
galactic
okay.
nuclei,
So
also
The,
those,
I mean,
nuclei. So
the
what
idea
you
that
see here
effective field theory is not
activity
UV
in the
complete is
center
because you
of
cannot go beyond
of
Planck
the-
scale.
Here is the galaxy. And it's a lot of energy coming out of the galaxy. And then if you zoom in and.
If there are no questions, I have a quick comment. Regarding the bending of light, that was not done by Feynman or David. It was done only in 2006 by Baron Bohr in Copenhagen.
I think
Yes,
there was
yeah.
even earlier results.
Really?
At 311, there are even earlier results.
Okay.
I think,
Using scattering amplitudes,
So
that did
it's-
it in 2000.
yeah, but this is the with loop corrections, right? I think 311, there are even earlier results.
Earlier?
At least I'm almost sure that Ascioli, for example, has
In
some work
69,
from the
then
90s.
Leon
Okay,
Bell
we will
And I
check
don't
that.
think he was the first one.
Okay, we will check that. And I see a typo there. In particle physics scale, you showed the Planck scale and particle physics. You have 10 to the 2 GeV. Make it 10 to the 4 GeV.
Where?
No. It's not. All galaxies are dead quasars.
Fourth from the last.
All quasars are active galaxies. All galaxies are dead quasars.
Yes, well,
That's 10 to the 4 GeV. So we are good until 10 TeV now.
So quasar.
here I was referring to
not
electric scale, not
speculated as
the,
a black hole
yeah,
system.
It's electronic scale, yes.
Activity radiates.
the electric scale,
Now,
okay.
the thing is that,
Questions?
and what about the quiet
Okay,
galaxies?
so maybe just
They also have
to
black
understand
holes.
this
Call that
asymptotic
the
safety.
quasar.
So
Okay, so normal galaxies.
you say that
can
you
call
postulate
quasar
this, I mean,
center.
scale invariant fixed point, and this
So now,
comes from a
as
phase
We
transition?
just saw.
The idea from a lattice
calculation
perspective
has
is that this would
been
correspond to a second
Actually,
order
it was
phase
So
transition.
confirmed
there's,
since
do we have any idea what
1995
this
through
phase
the
transition
observational
is? And then
measurements.
just to understand, like this phase
And,
transition would
around
be,
the galaxy,
as you lower the
and,
energy, you go through this
now
phase
all
transition,
galaxies contain a super-
then you have like your critical surface and which
notable
only has a
thing
finite number
was
of coupling constants,
years ago
and
through
that's
the
why you
Event
can
Horizon
somehow
telescope
have your
that
theory
saw
for quantum gravity, but
center
then
of the
maybe
black
it doesn't
hole
make sense,
in
my
the
question, but then if you go to
temperature
energies
7,
higher
which is
above,
a
like then you're
galaxy
still
in the
again somehow
Virgo cluster of
subject
galaxies,
to energies
around
which are below the
5
phase
million
transition,
light years
right?
away.
So
And
the idea is
So this is.
from this
we cannot
UV
see,
complete
but,
theory,
this is,
in the deep
fake,
UV,
uh,
you are at the
color.
fixed point.
But they could see in radio.
And then you will
this
stay at the critical
emission
surface
But-
when you
but-
flow towards the infrared.
black hole
I
region.
just don't get this picture, like usually you would say you have a
Percent
phase
is
transition and
very
there's
strong
like a
lensing, because what you have is a
energy
black
range
hole,
below and
have
above. But you
matter
somehow
around
say
the
there's
black hole.
nothing above the phase transition, like.
Light
it's
coming
not-
out of that matter. and
Yeah, I mean, the idea is to realize this is a fundamental
Circles,
theory.
because
So
the
you get there and you stay there.
You get them, you stay there,
very
but you
powerful
could,
gravitational field.
but then it's not really like a
They
phase
can
transition. It's like
light
you say that in
do
the
everything
UV, you're going to a critical
go
point,
around the
but
black
this is
hole.
like manifestly critical and you stop
so
there?
that's
Or
precisely
maybe,
what
that,
this is.
so
This is
maybe
light
it's just like confusion in my head, because normally like a phase transition is
from
you have a
the other
whatever,
side
a
of the
critical
black
temperature, and you have temperatures above, you have a certain phase there, and then you go through your critical point and you go to some,
Our
right?
galaxy
I don't think this
represented here.
picture would exactly apply here as a
the
fundamental
center of our
piece. I
galaxy.
think Antonio has some comment about
so it
this
wouldn't
stuff.
be really phase transition, it's just you go to
There
a
is
point that has
a
a scaling
famous
variance
star
and you're
which is
stuck
Yeah,
and
yeah,
the critical
so-
point.
When I mentioned the phase transition is because from the lattice perspective, this is identified as a second order
approaches.
picture.
But then you would have some energies
Has been
above
seen
the
approaching
critical
the-
point and energies
the
below the
also
critical
the-
point, right?
The
In this
Perry,
picture,
uh,
or is it,
whatever to
doesn't
the-
this
to the
make,
black
maybe
hole.
I'm thinking,
Yeah, I think Antonio has a better understanding
mean,
about that.
if you think
3 or 4
of
years
the
ago,
lattice as
maybe
really being
some
a
years
physical
more,
thing
yeah,
and not just a
people
device
used
to regularize the
things
theory,
due to the
then
gravitational field
your
of the
perspective is correct.
black hole.
like the scale above, you don't have any idea. So in this picture, you would just make a progress up to a certain scale, but beyond this, you're lost again.
Yeah, but for those that do, I mean, doing CD,
On top
causal
of
dynamical triangulations and so on,
Understanding the-
they take the discreteness or the lattice just as a regularization device.
I see.
There are those approaches like loop quantum gravity that you have a minimal length or a minimal area.
understanding that there is
And
a
for
massive black
those,
hole.
discreteness is fundamental. So there is really a physicality in this regime that you're referring to.
This redshift phenomenon.
Okay, thanks.
Now, there are black holes
You're not convinced.
Just
in the other
Any more
galaxy.
questions?
Every galaxy has a central
Just
black hole.
for the students that are not getting, Tobias works in condensed matter theory, and he works with renormalization group flow in another context. So he's trying to understand how these
71.
kind of methods that are very similar
And now
to
there
his
are-
own
there
are applied in this
Well,
context.
There are not many. I
Right.
think, 50 or so.
For the students to understand.
Observe through.
There was another
Telescopes. There are no more from gravitational waves. So this is, you cannot observe.
So
black
I suggest
hole.
the title to you and then,
This is a
okay,
black hole.
there was a unification of microcosm and macrocosm.
And,
But
what happens
yet,
is there is a distance.
even if you get
called an
unified
accretion
theory,
disk,
quantum
and
gravity
we
and other
start
things,
hitting this
there's
disk,
still something that maybe
because
you
it's
cannot unify the microcosm with
a lot of
macrocosm, because this
correlation of
implies some
energy
time,
between
some type of
X-rays and
reductionism.
X-rays
What I have in mind,
are
for instance,
detected,
if nuclear
then,
physics,
you look
okay,
better,
so we have
you see what's going
Kitsugi,
on, and
quantum chromodynamics, which explains
measure
the
orbital
really fundamental
star, and
aspects
deduce that
of
this
nuclear
thing is
interactions.
3, 4,
But
5, 10, 20
when you go,
kilometers,
for
then
instance,
you say,
construct
well,
an
that's
atomic
black
bomb, a
hole
nuclear
candidate.
bomb, nothing of that is relevant.
Well,
you
there was a
have
revolution.
A different framework, different concepts, different quantities.
Yeah.
There was
And
black
it's
hole
really,
coming out.
people don't know
Well,
how to relate
confirmation,
quantum chromodynamics to
of
the old
of black
nuclear
holes
physics,
themselves and
which,
of
because
from
people
stars.
construct the bomb
So
before
the first
knowing
detection, as we have
about
heard,
quantum.
was in
Well, what do you think about this?
September
So the
14,
question is,
and came
even
from
if
the
you have a
collision of
quantum gravity
roughly
theory, perhaps
233
it's not
solar
yet
masses
the
black hole
unification of microcosm
with
and
a final mass
macrocosm.
of 63.
Well, I mean, in this sense, the idea is
Radiated
you
was
try
three
to
solar
find
masses.
from
All
this perspective
activated
of
by general relativity.
unifying things in terms
And
of quantum gravity is to try
this
to find what are the
confirmed beyond any doubt.
building blocks. So
existence
the
But
fundamental
it's small, but this is small.
it's really small, but it does not mean that it's useful to do macro physics, right? Because
black hole,
as you said, in order to do nuclear physics,
black holes.
you have effective models that works better than trying to use.
Well, there is another
But
class.
the thing is
of black
that
holes.
you even don't know how to
Exactly.
relate.
And we don't know how to relate them. Yes,
black
yes,
holes
yes,
that come
that's
from,
true, that's true. So I mean,
collapse of stars.
what we know so far is that we do have
of
different
collapse of
regimes
clusters.
where there are the convenient degrees of freedom to describe
But
things.
it is
What are
expected,
the
well, black holes. can
convenient
also-
ingredients to describe things? You're
There
not
are
going to
no,
use quantum gravity to describe the free fall.
There
of
is
this
no law
bottle,
that
if I-
prohibits.
Yeah.
uh,
But
black
So
hole.
perhaps you need
Yeah.
a completely different
Do
concept
not
of
have black holes
gravitation
in the
in order to do that.
So they
That's
came,
what-
yeah,
they came from
We have a contribution from Felipe.
5 grams, which is Planck mass, to
Hi, very nice presentation, Gustavo. I have a quick question.
So-
In the asymptotic safety paradigm, you
you can
said
have in all scales.
existence of the fixed point is
speculating
very
that
important.
There are
concept.
primordial black
So
holes.
you said that there are
So
evidences about it. Can you
So
comment about it?
These are
Some
speculative,
evidence?
the ones were observed.
um,
After the Big Bang, small
as I said,
mini black
there are
holes,
some indications
dark
from
holes.
lattice, and that I don't know much about that.
And they would have, since the since the Big Bang.
Most of the evidences
and
come
so
from
in a sense,
functional
came out
renormalization
from
group
the
calculations.
fluctuations in the initial
And
concentration.
based on this kind of approximations where you
We are
truncate the
eager to
dynamics
detect these
and
black
solve the
holes
flow equation
until
under
now.
this truncation.
Uh,
And
and
what we see so far
But anyway,
is that at least a kind of numerical convergence on some of the
they
properties of
can.
fixed points if you increase the
Well,
size of the
another way
truncation.
is to
But, I mean,
replicate
that's not a proof
black
of
hole.
the existence of the fixed
So
point.
If we have
It's a
enough
fair
energy,
question
we
whether
can collide
adding
particles
things that are not in the
with
original
energy
truncation, if this
in a
spoils everything that you
precise
have.
place,
It's unclear if this
so
happens.
that the energy is
There are a bunch of
constant,
other technical
positively
issues
radiated,
like scheme dependencies and
rated,
so
and
on that
uniform
are not
radiated.
under control.
So one day we'll.
But
do
yeah, I
that
mean,
for sure.
original calculation from Reuter in the
So what
90s.
are the
to now,
physics properties of black holes?
I
So
think it's
now
fair
people
to say
start
that
away from a massive object.
at least we are more convinced
Burning
that
faster.
there's something. But now we need to
over the
convince
surface
others
of a
that
massive
there's
object.
something.
And
Thank
this
you very much.
is measured by the redshift,
Okay.
which is equal to
Sorry,
flowing
Nelson.
time
Okay,
far
I
away.
have a
and
response to
flowing of time
what you
in a
said.
given position.
So in quantum gravity, what we are trying to do is
for
reductionism,
instance,
right? But the other way is emergence. So Phil Anderson famously told more is different,
the surface
right?
of
So
the
just because we know
the
QCD,
redshift
we cannot make up
will
nuclear physics.
translate
So again, Ken Wilson
time.
taught us this effective field theories, right?
Um,
So we have this as input,
here,
but we can never start with
have,
fundamental with quantum gravity and then predict the weather. So it's never going to happen,
it's
even with a good
constant.
theory of quantum gravity.
The
So with good
surface is
theory
10
of
to
gravitation.
minus 6,
So
10
we
to
have to live with
minus
that fact.
6.
We can go down,
So
reductionism, and there is emergence.
And the
So
event
one
horizon
cannot
black
substitute
hole
the
is-
other.
is infinite.
So macrocosm is going to be there. We cannot explain a whole
So
of
the
macrocosm
mathematical
with a
expression
microcosm.
is given
Never.
by this,
F.
where our whole is 2gm over c square.
So, I mean, I just think that,
Math.
yeah, we also just say, well,
What's called the
integrate the
horizon
modes,
radius is
just
infinite.
integrate from the QCD scale
So you
to
see
nuclear
when
physics, and you are going to get
radius
what
of
you
the
want.
star is equal
But
to
of
the
course, I
radius
mean,
of the
in
hole,
practice,
then
we know
have
that
an
this is
infinite
just
equation.
impossible. So I agree with you that is impossible, but I just think that we also will say, well, integrate it. And you're going to have the effective field theory for nuclear physics from
No.
QCD.
Given that the redshift is given by this expression, when the star or the object has a radius equal or less than our
Could be
we
worse.
just saw that the redshift infinite and time stops at the event horizon for someone far away.
The question.
So in a sense, the black hole is black because nothing can
CBPF into the
that.
21st century.
And it's
But
also
the
a
question
hole
was
because
about
not even
the
like,
recent work in quantum
So
consciousness.
when this was understood,
So
one thought
that's
that
why I
something
said.
non-physical will happen
So
and that no object could become so small
I think
that its radius would be
Pronto.
equal to
The idea of
black
a
hole radius.
quantum theory
So
of
that
gravity
was the problem
would
since the structural
strengthen
solution.
the implications
structural
of the
solution
recently
has this
nominated
RH.
electromagnetism
When the
plus
star will
quantum
go to RH,
field in
everything will
humans.
blow up in
I
the
would
way that
guess he's
Schwarzschild
talking
wrote
about the hammer of thing
So
of quantum
people,
consciousness that
everybody
has
until
nothing to do with quantum
2000
gravity.
did not understand.
But thank you, Ricardo de Andrade.
So much later, it was
Right.
a following observer.
More questions?
When passing.
So just to
on
finish,
stage,
Gustavo, if you could, the last thing that you cited, you said your favorite thing. If I'm not mistaken, at the end of that meeting that we were together, we saw a calculation about confinements of ghosts in QCD.
Yeah.
Cannot come back.
So could you give an update on how constant ghost condensates in quantum gravity are going?
Collapse.
I don't have anything new to say about that. I can say that I'm very excited by that result. I think that, so
here
You
is
can talk about.
yeah, so the result that he's telling us
you
is
have a particle falling in.
a paper that came out
Cannot
recently
anymore
by
due to its singularity.
Manuel Ossore,
Result
Gaston Krain, and
travel around.
Ilya Shapiro.
If it passes.
And
inside
this was presented
the
in a
horizon.
conference in São Paulo
Yes,
a few
to
months ago. And what they did in there was to show that
Theorems were proved,
in a theory with
especially unique.
high derivative
final form of
terms,
black hole is
which
independent.
classically would have ghosts.
So one
Given certain properties, they could condensate into half
the angular
particles.
momentum and the
Um,
charge of the black hole.
And that resonates a
Will
lot with this
recall
idea of
that
Hodel
black
and
holes
Ring.
have
Although, I mean, in what we did in there was
why they have no hair.
related to super normalizable
They
theories.
have.
So I guess
have
that they
three
plan
hairs,
to
which are
apply
distinct.
this to super normalizable
Of
theories
course,
of quantum
someone
gravity.
with three
I think this
hairs
can also be
is
applied
considered
to
bald.
renormalizable
They have no
theories,
hair.
but
So
that's just what
Bruce said.
I guess. And I hope to show this at some point.
The area of the event horizon always increases.
Let's thank our speaker.
What is the
Thank you.
singularity made of? Well, Penrose said we should not.
For
worry.
those of you
Penrose
that
said
are on
because
BSCG tomorrow, 8:30,
there's
we're
no
all
law
back here.
that make it singular. Makes sense, cosmic censorship, but it's not proven. Well,
Yeah.
one could say that why don't we have white holes, which are the time reverse of black holes? The laws of physics are, in general relativity, are invariant under time going to minus time. So reversing time gives a solution, and the reversing of a black hole solution is a white hole solution. So in the white hole, everything comes out, nothing can go in. They were speculated to exist to explain quasars. There are some people that try to explain, but you know, they violate what is called the second law of thermodynamics, and they have been dismissed. Now, putting together quantum mechanics and general relativity, Hawking found in 1974 an amazing result. Actually, the black hole radiates particles to infinity, and with a temperature in Planck units, which is 1/m. And he actually made a calculation, which is very hard, which is a very hard calculation. But then he put out the idea that what is happening is that there is virtual particles near the horizon. And so it can happen that one particle that is created very near the horizon goes in, and the other particle flies out. And then another. So all the time the vacuum is giving particles in and out. Since you have to eject particles to the outer space and to infinity, then you see that black hole loses mass and the temperature rises, and loses mass and the temperature rises. So what happens to a black hole is that it's going to disappear in some time because it radiates energy. For solar mass black holes, this time is longer than the time of the universe. But for tiny black holes with masses very small, not so small, black holes with mass equal to the mass of a mountain, which is equal to 10 to 15 grams, so 10 to minus 18 solar masses, these black holes have temperatures of the order of 10 to the 12 degrees Kelvin. So they are very hot and radiate energy in the high energy spectrum of particles. Okay, then Hawking found that actually the Bekenstein speculation that the entropy of a black hole is equal to the area, it's correct. And he showed after the precise definition of temperature that the precise coefficient in front of A is 1/4. Okay, actually it should be 1, but then the Planck, because this is in Planck units, but then the Planck units should be different. And the Planck units, as they are usually written, gives 1/4. And so Bekenstein said that was proportional to A. Hawking discovered that it was 1/4. And correctly, it is called the Bekenstein-Hawking temperature. All of this is in Planck units, which are units that you can take from H, G, and C, which are the fundamental constants. These are very small, and the mass is very big. This is 10 to minus 13. The mass is 10 to minus 5 grams. Then came the black hole thermodynamics with the zero law, the first law, second law, and the third law. This was proven by Bardian, Carter, and Hawking in 73, before all this, actually not before the entropy. But then if you substitute S by this entropy and T by a Hawking temperature, then is actually 4 laws of thermodynamics. Before was 4 laws of black hole mechanics, but then started 4 laws of thermodynamics. In a recent paper with Fernandez, my student, we showed that, well, what people knew, but that these are really consistent. We proved that from statistical mechanics, so going to a canonical ensemble, and we showed that the first law of black hole mechanics can be derived directly from statistical mechanics. Well, there are several open problems. One is, well, the puzzles are entropy and information loss. So we know from statistical mechanics that entropy has to do with, is related to the degrees of freedom of a system, which is related to the phase space and then the degrees of freedom in phase space. And Boltzmann postulated that the entropy of a system is logarithmic of those of the volume of the phase space of that system. But in black holes, we don't know what are these degrees of freedom. So how can we relate the entropy to the degrees of freedom? Up to now, it's open. Actually, as I said, Toft started to try to understand that, but it's still open. So how does heat appear in a black hole? What moves in a black hole? People think that it is related to the movement of space-time quantum, the atoms of gravitation, but where they are in a black hole and what are they in a black hole? So this we have to understand. Another problem that it's still not solved is that what is called the information problem or the unitary problem. So if you start with a star collapsing and you have all the information, you can have all the information that is in the star, but then it collapses to a black hole and the black hole radiates away in Hawking radiation. And the Hawking radiation is thermal. So there is no information at all in Hawking radiation. So what was before, well, a lot of information on the star, about the star, disappears through the black hole. Now, quantum mechanics say that every process in physics is unitary. And so collapse of matter to a black hole in evaporation should be unitary, or that is, you don't have information loss. But here it's gravitation, so it's different. So maybe the singularity swallows information. Now there is a lot of work saying that there is no swallowing of information and the information is retrieved. So we are still trying to understand that. Now, well, what we can hope for the next 50 years. So general relativity opened these major new branches: gravitational lensing by Einstein, gravitational waves by Einstein, cosmology by Einstein, fundamental theories, that is unification of general relativity and gravitational theory with electromagnetism by Weil, and black holes by Oppenheimer-Snyder. The second, third, and fifth branches have now got gotten Nobel Prizes. So we have gravitational waves, cosmology, and black holes. So my guess is that soon we'll have gravitational lensing. It's going to get a Nobel Prize. And later, I think we'll also get someday a Nobel Prize in fundamental theories in this sense, that gravitation with other theories. Okay, so I think that this is the most interesting problem. Which theory will supersede general relativity? It's going to appear at extremely small scales or at extremely large scales. Surely the next 50 years will tell. I hope it's the next 20, so that maybe I'm here. Well, to finish, Anaximander, 2,500 years ago, proposed that the Earth is held up by nothing, but remains motionless, owing to the fact that it is equally distant from all other things. He said that its shape is like that of a drum. We walk on one of its flat surfaces, while the other is on the opposite side. And this statement, there are many few statements for Anaximander preserved directly. And this statement is considered one of the most portentous ideas in the whole history of human thought. Because at that time, he envisaged the Earth as freely poised in mid-space, remain motionless because of its equidistance to all other things. And in a certain sense, anticipates Newton's idea of gravitational forces. Now, 2,500 years after, we have the science of astrophysics and gravitation that can explain stars, black holes, galaxies, and large-scale structure of the universe, and the science of cosmology that can explain the universe itself. And so the whole of physics is involved: general relativity, condensed matter physics, atomic, nuclear, particle, and plasma physics. And here we are, happy and full of joy and glory in the 19th Brazilian School of Cosmology, celebrating the amazing understanding of physics and astrophysical black holes, to which in 2020 a Nobel Prize was first time awarded. Thank you.
Okay, questions?
It was a fantastic talk. Thank you.
Alô? 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 Alô?
Ele pode repetir, não? Eu vou falar. Ele pode repetir. Hello? Oh, yeah, see, it's okay. Thank you. It was a great talk. In one of the earlier slides, by the way, talk was very complete, right? From the beginning to the end, you covered the whole ground. In one of the earlier slides, you told we can have a trapped surface, but not necessarily a black hole, right? Under certain conditions. We can have a trapped surface, but not a black hole, right? Under what conditions?
Well, because trapped surface is local. So you can have trapped surface, all the way. And for instance, you can you can violate the energy condition, and at a certain stage, the weak energy condition is violated, and so you can disrupt the trap surfaces. And so for the theorem to hold, you have to have also the weak energy conditions to hold. And so we have trap surface all the way. But a trap surface is a local condition. And so you can have trap surface you can slice the space-time so that you have trap surfaces, but you don't have black holes.
So by black holes, you mean the event horizon, which is
By black holes, I mean an event horizon. So there is a last light ray that arrives at infinity.
See, trap surface is a local concept, and trap surface is a local concept, whereas the event horizon is a global concept, right?
That's right.
So we can have one without the other, okay, and one together with the other. Okay, got it. Thank you.
More questions? Students? Yes. Hello?
Maybe just a minor curiosity. On the previous slide, you were showing like gravitational waves, Einstein. Wasn't Einstein against the idea of gravitational waves? Like, didn't he made a paper saying that gravitational waves would never be detected or even exist? So why do you put Einstein on gravitational waves?
No, the first paper on gravitational waves is by Einstein in 1916. So he started the field.
Wasn't he saying that they wouldn't be detected?
No, that was after. So in 1916, he wrote a paper, but the paper is totally wrong because there is monopole radiation. But then people pointed out to him the mistake. Abraham, which was his colleague, and Nordström was a physicist in Finland, told him that it should be quadrupole. And then he wrote a paper in 1918 revising the monopole and saying that there is quadrupole. But even so, he got it wrong by a factor of 2. And so this factor of 2 appeared then in 1922 in a paper by Eddington. So the quadrupole formula for radiation was first time written correctly in 1922. And then there was a paper by him and Rosen that they said, so that's 1935, it was already in Princeton, that they said that there were no gravitational radiation. But then Robertson, the Robertson of Cosmology, of Robertson Walker, was referee of the paper and said that the paper was all wrong. And then Einstein was very upset and said that he will never publish again in PhysRev, but he accepted the criticisms via Infeld, to whom Robertson told, look, tell Einstein that it is wrong. And so Infeld then was friend of Einstein, explaining him carefully why he was wrong in that cylindrical waves. So it was gravitational cylindrical waves.
What was the thing done by Landau? Quadrupole formula? Or?
By Landau Landau and Lifshitz actually associated the far field with the near field, I think. That is in the
they were the first one to write down the quadrupole formula, not Eddington. Eddington fixed the problem in Einstein's. Maybe we can check this later.
Yeah, you can check that. But I think Eddington wrote the quadrupole formula correctly.
Can I? Professor, you spoke a little about spoke a lot about the thermodynamics of black holes. I have a more of a curiosity question, because when those laws were developed, the whole idea of black hole was still an idea and was not proven like nowadays. So And until to this day, like measuring, you said when we measure black hole entropy, we don't measure black hole entropy, and we probably will take a lot of time to measure something like that, right? So my question is more, why and how it became so much of a staple of fundamental physics that we all have to recover the entropy as you did in a recent paper, because it's a formula that's theoretically consistent and theoretically derived, but has no basis in observation. So it's a nice formula, it's a nice result, but until it gets an experiment that proves it, why is so important in the whole world of physics? Why so many people care so much about reproducing a formula that has no experimental backing?
Yeah, but you can ask that of everything that has no experiment. For instance, Einstein's equation at the time had no experimental. But why? So, but then it took, years when Sobral too, that was the first thing, but many people didn't believe. And so, so it takes a lot of time to go, in many cases, to go from a concept, a theory, then to have the experimental thing done. For instance, gravitational waves took from 1916, so the first paper by Einstein, until 1950, when people started, Bondi and Pirani and those guys, started to discuss really the reality of gravitational waves. Until then was nothing. So it's the same thing.
Interactions in the fields, it's not clear that it's even correct. Yeah. You have logarithmic correction.
Oh. Okay, let's take a game. Very nice. Now I have the last talk of the Brazilian School of Cosmology and Gravitation, but everyone is invited to stay here because it is Professor Amir Caldeira. We talk about instant and bounces, condensed matter in physics. And so it's something that relates many subjects together, join many subjects together.
If you want to test your black hole radiation, analog models is a way. Sorry. Okay,